Okay. Good morning, everyone. I am Kai Liu from Tsinghua University. Welcome to our series of virtual academic seminars to celebrate the launch of SmartMed. As a youth editorial member of SmartMed, I would like to introduce this journal at first. SmartMed is an open access journal co-launched by Yi and Tianjin University. The editor-chief of SmartMed are Professor Wenping Hu from Tianjin University and Professor Hua Zhang from the City University of Hong Kong. In my opinion, SmartMed is a young journal, but has a very, very potential journal focusing on the smart materials and smart devices. And also today, we are very lucky to have Professor Yi Long from the Nanyang Technological University to give a presentation. Her topic is also smart materials and smart devices, very well fitting well with the topic of this great journal. So now I'd like to briefly introduce the speaker first. Dr. Long graduated from Cambridge University in the United Kingdom. She is currently a senior lecturer in School of Material Science and Engineering at Nanyang Technological University. Her research is to develop smart functional materials by manipulating of the structure from nano to micro scales to achieve the unusual properties. She has published numerous great papers on high-profile journals like Jewel, Chemical Society Review, Advanced Energy Materials, and so on. So let's welcome Professor Yi Long. And Professor Yi Long, please. Thank you.
Thank you. Okay, so you can also see my mouse. Okay, thank you so much. Good morning, everyone. Yes. Yeah, okay, good morning. Yeah, thank you so much, Kai, and for your nice introduction. So because I only have 45 minutes, so I just try to cover as much as I can. So in this talk, I'm going to cover the responsive materials from energy-saving smart window to smart devices. Okay, just straight to the point. So this is my content. So I majorly divided into two parts. The first part is the smart thermochromic window. And the second one is stretchable electronics and artificial muscles. So you can say the majority of my talk will be focused on the smart window. So why the smart window is important? So let's just talk about the first one, the energy-saving smart windows. Okay, so this is the big picture. So you can see we published an invited review for AEM. So you can see from this graph, right? So 40% of the energy consumption is actually consumed in buildings. So actually, this is a very alarming figures. And among this 40%, so 50 is coming from air conditioning. So how can we, and also the window is the least energy efficient part. So how can we reduce the energy consumption through the windows? So smart window is one of the obvious options for research community and industry. So there are four types: electrochromic, thermochromic, mechochromic, and photochromic. So, and also there's another fact I have to put it here because I personally think this is really alarming. I was told this by my collaborator from US, and he told me that from the UE, Department of Energy of United States. So actually in United States, the national total primary energy consumption was about 97. So you can imagine this is total primary energy consumption. So it's 97. While window associated energy consumption in building was estimated at about 3.95. So you can say it's roughly about 4% of the energy is consumed through window. I only know this one about a few weeks ago. I was really horrified, and I double checked. This is really coming from the DOE, from the Department of Energy of the United States. So, which means that how can we reduce energy consumption through the window is of great practical. If you talk about this carbon neutral thing, which is quite hot topic recently. So how can we cut down this energy consumption through windows is really something worth a lot of efforts from the research community and also from the industry. And as I said, there are 4 types of smart window. I mean, the large amount of the smart window are from electrochromic, thermochromic, and the mechanical and the photo. And you can see thermochromic enjoy the passive actuation, and the stimulus is coming from the thermal, and the device is super simple, and it's very simple, and just simply you need the encapsulation, and it's very suitable for the NH smart window. And also it's the transition speed is also very acceptable for window, because window you don't really need very high speed, so it's a different concept. Okay, and also in this thermochromic smart window, there are these few type: hydrogel, ionic liquid, metal materials, perovskite, liquid crystal, and vanadium dioxide. Vanadium dioxide is most conventional one. So basically, I'm going to focus on this hydrogel and also the vanadium dioxide. Okay, so this is basic my research topic, and then I summarize what I'm going to cover here. So basically, you can see, so for smart window, you have electro, thermal, photo, and mechanical. So there's 4 type of smart window, and I focus on this thermal. And also, I only cover about vanadium dioxide and hydrogel. Okay, so just let you know, this is where I'm from, and this is a big picture of this whole talk. Okay, so I'm not saying all the other are not important. They're also important. Okay, and since I said I'm going to focus on hydrogel and also vanadium dioxide. So vanadium dioxide is a very famous near room temperature phase transition materials, because it's going to change from the rutile phase to monoclinic phase, and change from insulator to metallic state. Okay, and also hydrogel is another mechanism. Hydrogel is based on the phase separation. So you can say, because when you heat up, so certain of this polymer chain is going to shrink. Okay, once it shrinks, so it's going to change a lot of properties, including the optical properties. Okay, and our group started this whole thermochromic smart window about 10 years ago. So at that time, we learned tremendously from Prof. Gao Yanfeng's paper. This is a review paper, and we have to let you know if you're not in a thermochromic smart window. So as any other applications, there are some performance index. Okay, for performance index. So one is solar modulation. The other one is visible transmittance. So which means you need high visible transmittance and high solar modulation. So if without doing any structure modulation, so the singular is roughly here. So at that time, people introduced power structures, material structures, and composite materials. Okay, so all these things has already been introduced about 10 years ago. So then we start our research at that time. So we also have done a lot of research on the conventional ones, like nanocomposite, powers, and multi-layer one. But also at the same time, we're trying to think about new things to do. Okay, what we can contribute to this community. So then we say, hey, maybe we can, because we need to enhance this delta T cell and the T-Lu. So maybe we can introduce these graded structures and the photonic crystal structures, and also these biomimetic structures. Okay, so this is what we have contributed in this vanadium dioxide-based smart windows. And also, because after some time, we realize it's quite difficult to continue to increase properties. So we say, hey, everyone is doing organic or inorganic materials. Maybe we should try some organic materials. So one obviously is hydrogel, because hydrogel have very large modulation in this visible range, because the visible range have higher solar energy density. Okay, so we are the first one actually in this community to introduce this hydrogel in this research community. So one is organic, the other one is inorganic. So the next one is obvious, we just hybrid them, vanadium dioxide and hydrogel. This is a very standard way for material scientists to continue to increase the enhance the performance. Okay, then one day we said, hey, maybe only passive is not enough, because we found there's a bottleneck there. It's more and more difficult to continue to increase. So we think maybe, hey, we shouldn't just focus on passive anymore. So maybe we should include a little bit of active control, give them extra. extra stimulus. So we first introduced this electrothermochromic, which means we use some Joule heating to give them not only passive, but at the same time, this active control. So this is one. So then also maybe we can introduce some mica thermochromic. So we have a double stimulus. So this is going to enhance the properties tremendously. And also a little bit extension there. So the hydrogel, okay, as a material scientist, it's a very painful thing to upscale because of my unique experience, because I used to work for Seagate to do the lab to fab to transfer the technology industry. I know how difficult it is to have uniform, easy to upscale, because as a material scientist, it's always a very difficult thing to make large scale samples and to make it really work, because this is something which is very important. So last year we introduced this very strange concept like hydroliquid. So we are not using hydrogel anymore. We make a liquid. So you can imagine if it's a liquid, so basically it can just flow everywhere. So it's much easier to get very high uniform and large scale coatings. Okay. So basically, I'm also going to, so you can see these are the three big parts of my talk. So now I quickly move to the first one, the vanadium dioxide one. Okay, so the first one, the MOSI structures. So this is biomimetic one. Since I only have 45 minutes, so I don't really talk about details, okay, because the purpose of this talk is brainstorming. I really want to collaborate more with researchers all over the world. Okay, so I'm just talk about ideas. Okay, so the first idea is a MOSI. Then we talk about photonic crystal, and this is our latest paper, which is ghetto inspired anti-reflective structures. Okay, so the first one, this one is with Jilin University, because Jilin University, they are very good at making these MOSI structures. So they gave me this substrate, which is silica spheres. The silica. It's a silica and MOSI anti-reflective structures. Then we coat VO2 on top of it. So once we do so, we realize, hey, if we can make sure that periodicity is small enough, so we can enhance both Tiru and delta tissue at the same time. So this is our very first paper on this biomimetic nanostructures. Then we think, hey, because vanadium dioxide have a color which is brownish, and some people say, hey, we don't like the brownish color, so can you change for us? Yes, so we can use this also photonic crystal structures to change its color. So the concept is very straightforward. You know the butterfly, right? The butterfly. Why the butterfly have this colorful the colors, different colors, because they have these photonic crystals. So we just assemble these silica spheres on top of this glass, then we coat vanadium dioxide on it. So you can see then we can change the color with increasing with different like 200, 400, 600, 700. Okay, you can change the color. And also at the same time, we maintain a very good enough thermochromic properties. Okay, so we can see this is a color change, and this is simulation done with by my Israel collaborator. We know that why this is a change, because the reflection has changed. Okay, and then this is our latest paper. So because all these MOSI structures or photonic crystal structures, they have fixed periodicities. Okay, so which means they're very angle dependent. That's number one, and also they only change certain wavelengths. But there's another structures which we call a ghetto. So have you seen this ghetto before? It's I also for the first time I know it. So this ghetto actually is also butterfly, but its wing is super transparent. Why is so? It's because if you examine the structures very carefully, we see they also have this more or less like MOSI structures. But okay, the difference between the ghetto structures and the MOSI structures is because the pitch, which means from one side to one peak to the other peak, the periodicity, if for MOSI is going to fixed. Okay, but for ghetto is actually sort of random. So which means your pitch size and pitch height is randomly distributed. So you can imagine, actually, this is very difficult to realize, am I right? To experimentally, am I correct? Okay. Okay, so because you maybe sometime if you want to fix this pitch and fix height is even easier for material scientists. So we come out very strange ideas. So first of all, we just align this silver nanowires. Silver nanowires is only about 15 nanometer. So we're trying to align monolayer on top, then form this template. So we call it template structures. Okay. So once we have this template, then we try to coat on top of because we want to say this is a universal, robust bottom way to replicate these ghetto structures. So we try two systems. So one is silica, one is vanadium dioxide. Okay, so you can see by doing so, simply actually if we control the speed of this spring, the spring, and also the viscosities, so we can control actually the mean height and the mean pitch. Okay, so that's also something very interesting. Okay, so you can see we sort of mimic the ghetto structures. Okay, so why we need ghetto? Because once we have ghetto, as I said, right, so you can say we have this fitting the average height and average pitch. This can also be controlled by the spin speed and also the deposition time. Okay, so it's a very simple concept. Am I correct? So you can just simply you need to have a beaker. You simply just need a beaker and a stirrer, magnetic stirrer. Then it's pretty enough for you to have this template-based approach. So personally, I think this is a very, very interesting paper. So you can see we have done the TEM. So this is silver nanowires. On top, we have vanadium dioxide. So the other thing is because once you have ghetto structures, so it's become this anti-reflection. So is angle independent. So this is also very important, right? It's angle independent because if you have more size structures, they have certain angle. So a certain angle have better anti-reflection, but some others is not. So this one is actually very, very useful if you think about solar cells and all these many applications, because they want trap or as much light as they can. So they don't want angle dependent. They want all the scatter light can be get trapped. So this is also a very useful way. And also from our thermochromic properties, we said once we have this introduce this template, so we can enhance again T-room and delta T-room at the same time. Okay, so this is some earlier work. Okay, so I finished this biomimetic one. So biomimetic, we have mosaic, we have butterfly, the photonic crystal, and this ghetto inspired anti-reflective coatings. Okay, so we quickly move towards some new ways, we use FTTT, collaborating with my Israel partner. So we know once we created all these graded structures, we can also enhance this T2 modalities at the same time. And also then my student went to Israel because she is a double degree, which means she has 2 degrees from both Singapore and Israel. She used this electro deposition way to coat on top of this to just directly deposit this vanadium dioxide on the graded structures. And by doing so, we can get much enhanced T-room and delta T-cell at the same time. And also, this is another way. The student Luci, just my FYP final year, he's just an undergraduate student. He also come out very simple way, just use a mesh. So this is a mesh. Just a deep coating, just drip on top of this something just with vanadium dioxide by self-assembly. So it's going to form these graded structures, and also it's going to enhance T2 and delta T-cell dramatically. So you can say this is a very simple concept. So it's very good for just undergraduate students to do such thing and make them feel a sense of satisfaction. It's a very simple way, and also it's effective. That's the most important thing. Okay, and the other thing is vanadium dioxide also have a very interesting, we call it's a tunable plasmonic effects. So people who are doing the plasmonic, plasmonic only occurs in metal state, am I correct? But vanadium dioxide, as I said before, because it's a near room temperature phase transition materials, because it can change from metallic to insulator. So which means this plasmonic effects can also be tunable. So first of all, why we need two plasmonic effects? Because this is solar energy density. So you can see solar energy density have a different density on different wavelengths. So obviously, if you want a very large solar modulation, you prefer your large modulation is occur at this higher densified solar energy area. Am I correct? Okay, so this is justification why we need to study this plasmonic LSPR. We call plasmonic effects of this tunable vanadium dioxide. So we also come out a method use a PS sphere. So we simply just control the PS sphere, the durations and the etching time. Again, some very simple ways. So we can get this nanoparticle with different periodicity, nano net, and nano dome structures. So also structures with different periodicities can be fabricated. This is a process. So this is a PS sphere we just assembled. Then we put vanadium dioxide on top of it. Then we just get rid of these PS spheres. So we can get all sorts of different structures. Okay, so as you have already seen, by SEM, we can really do it. So the interesting thing is here is once, because vanadium dioxide lovely have this tunable phase change. So we can tune this LSPR by simply either have higher temperature or give them a little bit more electricity, so we can switch on and switch off. Okay, and also this is a very interesting work. Okay, and then also since I'm a smart material guy, so we have to also demonstrate whether this is going to be a good way to enhance thermochromic properties, and it is true. Okay, so by doing so, we can also get both enhanced thermochromic properties, T2 and delta T. So. Okay, so then my student keep continuing because he want to study a little bit more. So he keep continuing change these dopants and oxygen vacancies and oxidations. We're trying to understand how these atomic defects, and also trying to quantitatively understand the atomic defects between these defects and the plasmonic characteristics. So this paper we worked together with Prof. Sun Xue Mei, I think Sun Xue Mei, yeah, from Nanhan. And she also helped us to find out that by using this DFT, and they revealed that the charge of cation plays a dominant role compared with others to determine the free electron concentrations. Okay, this part is pretty physics. So I collaborate well with my collaborator from Beihang. Okay. So, and also by doing so, we have achieved the record high tunability for the local LSPR. Like you can change the energy change from 0.66 to 1.16 eV, and the transition temperature, which is can even larger, 60 degree at intervals. And we have demonstrated different applications in smart window, variable camouflage, and the SIRS, and also the encryptome ink. Okay, so you can see the simple idea here is once you have this smart ideas of this vanadium dioxide, so actually its application is a lot. Okay, it's really waiting for all the researchers to explore how it can be used in various applications. Okay, so we just give you some ideas. Maybe you can try camouflage, try SIRS, or try this encryptome ink. Okay, so there's a lot of applications which can be done by this vanadium dioxide. Okay, and then we have together with Prof. Gao Yanfeng, we wrote a review paper for this Zhu thermochromic vanadium dioxide for energy efficient smart windows. So we review from this atomic level to nano level, electronic to nano level to micro level, to lab level, and also the real application level. So different levels, we just trying to understand and also review what's the progress of this vanadium dioxide to this research community. And this is the performance summaries, and some are the theoretic value, some are from experimental. So all these things, the tip one is from my group. Okay, so I quickly move to the second one, which is hydrogel. So as I said, this is just a very, because after some time, we realize it's really difficult to keep improving the performance of vanadium dioxide because of this intrinsic physics barriers. Okay, so we think, hey, why not we try some organic materials? But this is a very simple idea actually. So it's just a hydrogel. Okay, the hydrogel, because they can change in the visible range. Why we need change a little bit in the visible range? Because visible range have higher solar energy densities. Okay, so this is the very first paper. You can see it's actually very simple. Very quickly we can just laminate hydrogel between two glasses, and very quickly we can see here, compare with vanadium dioxide, we can get delta T-SO 20 compared with VO2 only 12, and the average 2 is 73, and to VO2 is only 60. So you can see by simply applying a very thin layer of hydrogel between the glasses, we can quickly enhance both TU and the delta T-SO at the same time. And then we continue because hydrogel, suffered from very poor mechanical properties, right? So we're trying to hybrid with the silicon aluminum matrix. It's also another gel, but it's not organic gel anymore. It is sort of like silica gel, so it's an inorganic gel, because in inorganic gel they have certain mechanical properties. So once we hybrid with the silicon aluminum gel, so we can print this silicon aluminum gel on top of this transparent electrode. Okay, so by doing so, also at the same time we can get much better durability, so up to certain cycles, and also we have very good so you can see thermochemical properties. Okay, and then the next one, as I said, is a very typical one for material scientists. Once you finish the hydrogel, the organic and the inorganic, so the next obvious thing for you to do is the hybrid. Okay, so you can see this one. This is vanadium dioxide, the very typical vanadium dioxide, and this black one, which is a very typical of hydrogel. So once we put these two together, so we can radically enhance this modulation. This blue one is a hybrid, so modulation you can reach to 34.7. Okay, so this is definitely one of the highest one at that time. I think it's 2015. Okay, so this is very obvious work after we have done a lot of organic and inorganic. Okay, so this is a new paper, actually. It's published last year. So because, as I said, since I have a lot of experience with industry scale up, I know how painful if you want to produce some very uniform structures. Okay, so, and also there's another scientific thing here, is because water, excuse me, so the water have extremely high specific heat capacity and also very large thermal energy storage capabilities. Okay, the PCM, maybe some of you have heard about this PCM, phase change materials, because phase change materials has been used as thermal storage materials. Okay, it has been used in building, but nobody have used it in window before, right? Because why is so? Because most of them are not transparent. Okay, once it's not transparent, you cannot use in windows. Okay, like also a lot of phase change materials has already been used in concrete and the walls already. Okay, so we think, hey, why not we use it in the windows? Because this water intrinsically have very high specific heat capacity and very high thermal energy storage. Okay, and the other thing of the hydrogel is because 95% of hydrogel is made from liquid. Okay, so that is what we do. Okay, we're trying to make a hydro liquid. So it's not hydrogel anymore. It is actually a liquid. So why you need a liquid? Once it's a liquid, right, you can simply just pour between two glass panels. So which means it's very easy for you. Even your window have very odd shape, can flow everywhere. And also you're going to have very high uniformities. Okay, so this is what we have done in Create in Singapore. So you can see this window glass is 1 meter by 1 meter. So you can see when the temperature up to because this transition temperature is about 30, so it can start to change into translucent. And even if high, it can be very opaque. Okay, this is me. I stand behind. I'm 1.6 meter. So you can see this is about 1 meter by 1 meter. So it's very uniform and it's very easy to upscale. Okay, so this is the first thing. We solve something by using a very odd way to provide some very out of box solutions to the research community. Don't just doing all this organic, inorganic. It's so difficult to get upskilled. So maybe we can try something new. And the good thing is we have also done a lot of simulations and demonstrations. We know once you combine the thermochromic properties plus this heat capacity, heat store, very high heat storage capacities. Okay, as I said, right, water, remember water, right? Water have very high thermal heat capacity. Okay, once you combine these two together, you get even better energy saving capabilities. Okay, so the other thing is you can see this is from the demonstration. So without any just a bare glass. So because Singapore, because the hottest time is about 12 o'clock. So the peak hour is happen at about 12 o'clock. But once we put our thermal storage very large heat capacity materials in between, so we can shift this peak to some 2 p.m. or 3 p.m. So why this is meaningful? Because this is actually where this PCM from, because of this change material from, because PCM can store the heat and can release later to some other time, why other time is important? Because the different time is going to have different price of electricity. Maybe 12 o'clock is the most expensive one. If you shift to 2 p.m. or 3 p.m., so the energy consumption will be much less. The price will be less. Okay, so this is a peak shifting. This is coming from the heat storage capabilities. And also we have done a lot of calculations. We said if we compare with those materials with either only have this thermal regulation, which is just liquid, or you don't have any combined effects from the thermochromic and the heat capacity, the phase change materials. So our materials, this 1 cm liquid, enjoy the highest energy saving. Okay, this is the data we have published last year. Okay. Okay, now I move to the active control. Okay, so the active control this is our first paper in 2016, collaborating with my Israel partner, Israel collaborator Prof. Shlomo, because he is expert on this transparent electrode. So since he's expert on transparent electrode, so we say, why not? We just work together, make our materials not only passive, but also active. Okay, so this is a very simple concept. Just use Joule heating because it's transparent Joule heating, so we can actively control either it's transparent or translucent. Okay, so we also are trying to demonstrate because we want to compete with electrochromic, because electrochromic is obviously the one of the most expensive materials now available in the market. So we see here we also have the similar the functionalities as electrochromic because we can enjoy much lower response time, and also the transmittance contrast is a much higher compared with most electrochromic materials. Okay. Then we continue. So as I said, this is a 3D printed hydrogel. It's a hybrid hydrogel. So you can see we can make it very expandable, like 180-degree bendable, and also have very high response time, with very fast response time, and also very low applied voltage. Okay, this is again we're trying to compete with electrochromic, and also this is something interesting. We can make it as an electro light guide, a little bit like optical fiber. Okay, so we just want to demonstrate that something extra we can do. Okay, so then my student Yi, he's a very smart boy, and he trying to say, hey, again, it's so difficult, right? Heat continue to increase. So he say, why not? We just introduce mechanical. So mechanical as one of the extra force to further enhance its properties. So this is he trying to use these kirigami structures. So once you have kirigami structures, so you can imagine in winter we're trying to open up. So obviously you're going to have a much better solar incident inside the through the window. Okay, so you can see this is a very typical one. So this state is a closed state. Simply just this is summer. Okay, so all this is coming from vanadium dioxide. Okay, so if without just open up, so this is a very typical state 2 of vanadium dioxide. Okay, but once we stretch, okay, so we can largely enhance this sterility. So okay, so we compare with a planar form, and also if you only have LSPR, which means you only have vanadium dioxide. oxide. And also if you only have kirigami, which means if you only apply this mechanical strength and stress, okay, so compare with them once we combine the LSPR vanadium oxide and also the kirigami structures, okay, so we can enjoy both enhanced delta Tissot and enhanced Tiru at the same time. Okay, so this is another concept. So as I said, in this whole talk, we're just trying to brainstorming and trying to introduce some strange ideas, trying to let people think what we can collaborate and what we can do, extend this whole areas. And also by doing so, we can say all this is from the vanadium oxide materials, and some are the simulation work, some are experimental work, and the best one is roughly here. This is actually, I think, is from the simulations, okay? But once we apply a new stimulus, it's very easy. Actually, this is very easy to break the boundaries. Just break through to give more than like 35 delta Tissot and 40% of the TU, okay? And Yi is he's very much focused on this mechanical stimulus. Okay, so also this is our also quite latest paper. So you can see this is a liquid. This one is a squid. You know why squid can change color? Okay, because once they get stressed, so these structures is going to shrink. You can see the pitch in between is going to become much smaller, right? So by doing so, which means you're going to have a different optical response. Okay, I think in this paper there's something which is very useful for our research community is, so you have to bear in mind, so what you can see, actually what eyes you can see is actually direct incident. Am I correct? Okay, so it's a direct incident. Okay, but actually what you can feel as a body, so it's the scattered light. So which means when you measure these optical properties, you have to differentiate either it is a direct line or it is a scattered line. Okay, so for the direct line, actually it is the privacy mode, which is what your eyes can see, where your eyes can see. But for this scattered light, actually is what your body can feel. So this is more, so this mode is energy saving mode, so energy consumption mode, and this mode is actually the privacy mode, which means what your eyes can see. Okay, so these two are different. So Yi has done this the surface structure modulations on top. So you can see, I just let you see this. Okay. The privacy mode and the transparency mode, but actually it doesn't matter. Both modes actually enjoy the same energy saving. Because why is so? Because the energy saving is coming from where? Energy saving is coming from the scattered light. But what your eyes can see is only the straight line, the straight one. Okay. So anyway, so you can just we have demonstrated the privacy mode, and because privacy mode is a straight one, and also we demonstrate this energy saving mode, so which is scattered one. Okay, so by doing so, we can say regardless of the stretch or not stretch, so you can always enjoy similar amount of energy saving performance. Okay, but what you can feel from your eyes is different. Okay, so this is Nikkei comic and the thermal comic. So these two modes are controlled independently. Okay, so perspectives. Okay, I think people is going to. So we have done this for nearly about 10 years. So the AEM invited me to write review on top. So I say here, what's the next? What's the next? Okay, so first of all, so we have to break the boundary between different categories, because as I said, we have 4 different types of smart window, right? Can we break the boundary between? So as I demonstrated before, we have already break the boundary between the thermal and the electrical, and also break the boundary between the thermal and the electrical. Okay, so can we still further to enhance? And also you need to consider the heat transfer through the windows, and also the scalability and durability. This is always is a perpetual issues for all the material scientists. How can we scale up? How can we make it durable? And also maybe some customer design and some multifunctional design. So this is what we think may be useful for the research community to further on. Okay. I just quickly summarize what our latest papers. Okay, so this is we're trying to consider the heat transfer. So basically, so Chen Zhi helped me to demonstrate. Again, use some very simple way. So this is a bamboo. So we use a bamboo. Okay, so this bamboo once we delignify, so we can make it very transparent materials, then we coat this silver on top of it. So by doing so, we can get a very high radiant cooling, which means now we consider the radiant cooling in windows. This actually is the first paper. So we can see by doing so, we can have very high RC thermal radiation cooling in summer. So you can see one portion, this side. This side is RC cellulose one, which is the one which is facing the indoor, face the room. So the emissivity is only 0.3, but the RC, which is glass one, which is facing the outdoor. So because we want enhanced RC, so by applying such coating film on the window in Singapore, so we calculated we can save up to 40% of the energy consumptions compared with commercial low-E glass. Okay, so this is one of the latest papers. And also, this one is a collaboration with Zhou Xin. He's from Sichuan. I think it's Chengdu Dianzi Daxue. I can't remember exactly. He's my exchange student, visiting student, and came to my lab for 1 year. He did a fantastic work. So they come up some way, just follow up by room temperature sputtering first, then followed by the rapid thermal annealing, very rapid annealing. So they come out such structures such as vanadium is more or less like nanoparticles embedded in some vanadium V2O5 and V3O7 as a matrix, and on top you have a very thin layer of V2O5. So why this one is good? Because once you have V2O5, you know the V2O5 vanadium dioxide is the most thermodynamic stable materials, right? So by doing so, we can largely enhance this vanadium dioxide, this coating's durabilities. I think it's 23 years, if I'm not wrong. Yeah, they have done this X-ray test. So we said it's about 23 years. So they have studied a lot. So you can see at this top surface, which is V2O5, which is amorphous V2O5, then VO2 is inversely distributed among this V2O5 matrix. Okay, so this is more or less like, because as you know that once you use PVD, you can only, most of people, the fabricate is a continuous vanadium dioxide films. But using such a very simple way, you can put the VO2 as a composite, as a like additives embedded inside the vanadium V2O5 matrix. By doing so, you are going to have very high durabilities. Okay, and also this is one of the customer designs. So we also want to say, okay, because in the research community, people always think that the light is coming at the same direction, but actually it's not true, especially for China, like in Beijing, the summer and the winter, because the incident light is the angle is going to be very different. Okay, so we use 3D printing. We use a 3D printing, okay, the 3D printing way, and trying to print at different angles, 0 degree, 50 degrees, 30 degree, okay. So why doing so? Okay, the concept is also very, very simple. So we're trying to, like a winter time, we're trying to let the sunlight go in this way, winter time, okay, which is something like this. Okay, it's trying to let the light come in as much as it can. But summertime, because the sun is going to have a tilted angle now. So by doing so, you are going to have much enhanced ability. So because you can imagine, because we introduce one new factors here, which is we measure the solar response at different angle, at different temperatures. Okay, by doing so, actually from this one, you're going to have a lot of research directly. I mean, a lot of ideas can come from this design. Okay, if once you introduce this different tilted angle, you have actually for physics people, it's very easy to do. Okay, so different angle, summer have one angle, winter have another angle. So the principle is just trying to let as much sunlight go in winter, block as much as you can in summer. Because at the different angles, you're going to have a lot of design here. Actually, there's a lot of room here to improve. Okay. Okay, and also the last word for VO2, we write review for small. You can say because vanadium dioxide, this phase transition from insulator to metal, it can be stimulated not only by heat, but can also be by magnetic, by electrochemistry, by electrical, by magnetic, okay, by light. Okay, so all these things can actually induce this vanadium dioxide phase transition. Okay, this is number one thing. So you can imagine. So, and also the output since it changed from insulator to metal, so it's not only the optical response has changed, like everything changed normally, like even your electrical response changed, the mechanical response changed. Okay, so we have come up with this review. So please, if you have time, you can read it because this is very much related to smart materials. So vanadium dioxide, how versatile this vanadium dioxide can be used in all sorts of like 1, 2, 3, 4, 5, nearly more than 20 different applications, not only for smart windows. Okay, our group only focus on smart window, but actually can be used for so many other things. Okay, so I just draw your attention on this review paper. So it's a very good one. Okay, so I quickly, Kai, how many more time I have here? Okay, anyway.
Oh yeah, we don't have limit. We don't have the time limited. So
okay. Can I just trying to run fast? Okay, thank you. Okay, so the part 2 is actually we are very much focused on our next 5 years. So how can we make it extend all these smart windows to like stretchable electronics and also artificial muscles? Okay, so and this paper is collaborated with Chen Xiaodong from my school, and we simply have this hydrogel we soak in the salt. So once we soak in the salt, so we can largely enhance its this mechanical strength. Okay, so you can see now we can enjoy much enhance this Young's modulus, and also the toughness is much enhanced. So this is very much wanted in like artificial muscles. Okay, so I show you a video. So you can see, because once we have soaked in the salt, so it can have very high ionic conductivity. So you can still, even your band, you can still have we can still conduct the electricity. This one is ion conducting. Okay, you can still become conducting, and also you can use as a pressure sensor. Okay, so this. Yeah, okay, so this is our 2008 paper. Okay, so actually my group is also going to put some efforts in this research directions in our next 5 years. Okay, so, and also this is a new paper. It's not a new paper, and also we have come out the way. So Hebing, he is trained in France, and he's very good at this monolayer, this 1D monolayer, this assembly. So again, he come out the very simple way. Just as I said before, you just need a beaker, and also you just need a magnetic stirrer. Very simple. Any group, all over the world, you can do it. Very simple. You're just trying to stir your nanowires, silver nanowires on top of it. Okay, your silver nanowires inside this solution. You just use a different speed. You can control the alignment of the silver nanowires. You can see this is very good. Actually, it's very good alignment, because this is one layer of alignment of silver nanowires, and this is 2 layers. Okay, because we assemble one layer first, then we just change the direction, a second one. Okay, so why this is important? Why we need a monolayer assembly? Because once you have a monolayer assembly, so you're going to have much enhanced transmittance. Am I correct? Okay, because now it's very ordered, and also this very monolayer assembled materials actually is going to reduce a lot of junction resistance. So your conductivity will be much higher. Okay, so that's what we're seeing here. So we compare with all these other electro conductors, the transparent conductors, like all these papers actually is from like Nature Baby papers, AM, all this from very top journals. Okay, so compare with all these other categories, people use CNT, use gold, use all the other techniques. So we can have much enhanced, we have the highest conductivity and the highest transparency, and also the highest stretchabilities. Okay, one of the highest, if I'm not sure, because now it's 2012, 21. At that time, we had the highest among all these 3 categories. Okay, so it makes this a good technology for this stretchable electrical transparent electrode. Okay, and also by doing so, we are actually introducing a new way for this monolayer alignment. So you can see we have write a review paper for Chemical Society Review in plane align assembly of 1D nano object Okay, so there's 10 different ways to can only have this in plane alignment. Okay, so which means this method you can only align on one direction. Okay, but all these other 11 different approach can use to make multi-layered architectures. Okay, so our one is the newest one. Okay, we introduce a very simple concept. You just need a beaker, you just need a stirrer, and you just need to fabricate some like 7 nanowires. You can make a lot of things here. Okay. Okay, so I'm done nearly. Okay, so summaries. Okay, it's just a small advertisement. Prof. Gao Yunfu and myself wrote a book, vanadium dioxide-based thermocomic smart window. It is you're encouraged to buy. Okay, and also our work has been highlighted everywhere. So this is reported in Nature. So Nature just reported our work, our group work about window, because as I said, window associated energy consumption is about 4%. So just bear this figure in mind, then you will know how important this research direction is. And our work has been covered by Reuters, World Economic Forum, CNA, Japan, everywhere. And more than 80 media in the world have reported our work. Okay. And this is my group, my funding. Of course, first of all, thanks all the fundings from NIF, National Research Foundation Singapore, MOE, Ministry of Education, blah, blah, blah. And also my friends. All these are my friends, okay? Because Dr. Ling, he left, so we have a farewell dinner for him, and they're all my friends, okay? I appreciate all the hard work they have been working with me, because I'm a little bit slave driver, but I appreciate they can tolerate with my bad temper, and we deliver a good work here. And also my collaborators. My collaborators are so many collaborators all over the world. China, I have a lot of friends in China. Actually, I haven't met them from most of them I haven't met, because research is very simple. You just write email. You need any support, you just write emails. Actually, I should add a few more in China and also in the States, okay, because we have some current work on progress. Okay, a lot of collaborations, and many of them I have never even met them. Okay, and this is some cover report of our work, and thank you. And all my best wishes to the new journal, the Smart Materials. 祝你们大卖大发。Thank you.
Okay, thank you, Yi, for your nice talk. Well, it's your work actually, in my opinion, is very impressive and also very systematic. Yeah, focusing on the many smart materials, like in organic materials, vanadium dioxide, and some polymer materials, also stretchable materials, and also as well as their electronics devices. So actually, I personally have some questions, like, you talk about the camouflage. So what kind of mechanism did you use to make the camouflage materials?
Actually, with our group, we haven't done any camouflage, but we have read some papers. The most of camouflage is coming from this the emissivity change in the long wavelength. Yeah. So because vanadium dioxide. Yes, exactly, vanadium dioxide. I'm not sure which category here. Must be somewhere here. Okay, so they use because emissivity of the vanadium dioxide is going to change. So with temperatures and with electricities, so it can be used in camouflage. Yeah. Actually, I have some work, but I didn't report here. Sorry. Yeah, I have some, but the principle of camouflage is coming from the long wavelength. Which is from this 2.5 micron to 25 micron. It's different wavelengths.
Oh.
Yeah.
You also use some liquid to make a smart window, right?
Yeah.
That work is very interesting.
Yeah, we actually
the thermal energy storage capability is actually is a key parameter for this kind of material. So But when the liquid is heated up and it must be cooled down to change its color, right? But the time may be long this stage. So how do you consider that factor?
Okay, so this is a good question. Okay, so first of all, we have to say this is the first paper to combine this thermal regulation, which is thermochromic, plus this heat storage capability. So this is two things work together. Okay, so you can see from here, right? Because we can change. Okay. So in terms of time, depend on the thickness. So once if it's very thin, so it's going to change very fast. Okay, so if it's very thick, so it's going to take some time. So you can see from here, we nearly take about one and a half an hour. So, but the thing is, so all this you can tune, because in this tau C here, the transition temperature here is about 31. So let's say if you want change earlier or change faster, maybe you can just reduce this tau C. Okay, this transition temperature, you can reduce it. So, and also the other thing is for the window, right? So window is not like a device, like an optical device or like a storage materials. Okay, window actually is not that much sensitive to the change of time. So how fast your material can change, So compare with the other applications. Some other applications, they need very fast transition. But for window, this part is more tolerated. Yes.
Yeah.
Yeah, I agree with you. You can see from here it's about you start to change about it's 1 hour, 1 hour already. And also simply because the temperature hasn't rise up yet. Because at that day, Singapore is a quite cool day, that day. So we didn't expect like noon sunshine that day. So that's why it take a bit longer. So all this is actually is up to the climate, up to the geometry, where the geography where you are, the location and the weather of that day, But the good thing is it's all changeable. Yeah. But it's a good question. Yeah, I totally agree with you. So once you want use this heat capacity, if you want to use this characteristic, you have to suffer a little bit of this fast transition of these phase change materials. Yeah, I totally agree with you.
Yes.
Mm-mm.
So can this temperature, it also depends on the phase transition of this material, right?
Yeah, exactly. So we can reduce phase transition temperature even like 20. There's no problem. No, so it's completely depend on the customer requirement. So what's the requirement? Yeah. But as a material scientist, this is easy, easy to do.
I see. Yeah, for the talk for the content about the durability. So you use the VO2, right? VO2 and also use the structure, the schematic for the structure. It seems your VO2 and it's wrapped by some other vanadium oxides.
Yeah.
And V2O5, I know it's stable because vanadium has the highest valence in this component, in this material. But V3O7 I guess it's not the stablest phase for vanadium oxides. So is it possible to be oxidized when during your durability test? I mean,
I can't remember. I have to check the paper again. I can't remember after durability test whether the V3O7 has changed to the V2O5. I have to check back. But when we do the durability test, right, we just measure the UV-Vis, the T2 and delta T cell. Okay, so if we say after like how many cycles, how many days of X-ray test, if the delta T cell and T2 is still roughly the same, like less than 10% of the degradation, so we said it is still very durable. So I think this paper we have some equations to calculate, and it's about the 23 years. Okay, so this method is reported by Cao Xun before, Cao Xun from CES. Chinese. Yeah. Reported some like X-ray test method. So we follow his way to measure it. So we say we report is 23 years. Yeah. So so back to your question. So even this V3O7 converted to V2O5, it does not. The most important thing is VO2 has been protected. So that's the most important thing. The other thing is because you see we have V2O5 on top. And you see, actually the V2O5, the morphosphere is on top already. So it's more or less like Big Brother to protect everyone. So that's so it's a new strategy. So why this work we think is quite important is because when you use PVD, right? When you use any PVD method, so almost all of us, what they do is you're just simply code continuous VO2 materials. Am I correct? So the next thing people maybe do is just put some protective layers, the multi-layer structures. Okay, so this is most of the only ways people are doing at this moment. So the problem for the continuous VO2, so the performance is also always very low. The maximum, if you continuous VO2, I think the maximum is only about 12% of the LT. But once it becomes a nanocomposite, so once the VO2 is not a continuous film anymore, VO2 become more or less like particles. So once you imagine it become a particle, it's a little bit like a nanocomposite. So which means the nanocomposite concept of the VO2 is VO2 become a particle. So it's going to reduce a lot of scatterings and also reduce a lot of absorptions. Yeah, so by doing so, we can also enhance its delta so and TLU at the same time. So it's not only about durability. The thermochromic property is also very good. We have a comparison, but I didn't put it here because, as I said, so this talk is more or less like a brainstorming. So to just encourage people to work more together.
Okay. So I think the smart window, that such kind of in smart windows, the use of smart materials and also smart devices is actually a very promising research field in the community of smart materials. So do you have any words to maybe recruit some students from the China mainland? Do you have some words to say?
Oh yeah, hi. Actually, just back to this Zhou Xing. We have an excellent collaboration. Although I criticize him all the time, but I'm very bad tempered person. I'm just joking anyway, but that's true. Okay, so Zhou Xing is a visiting scholar from China. He's from Chengdu 电子科大, I think so.
Yes.
Yeah. So he got the CSC, right? Chinese, some I forgot the name, 中国留学基金. He got 1 year sponsor and he joined my lab for 1 year. So actually he's also continued working with me and he went back to China, but we are continue to collaborate further. And I think now he stays. So I definitely welcome China students. They're excellent. And they are so hardworking.
Do you still have any plan to recruit more Chinese students in the near future?
Yeah, why not? I still have one opening for PhD student. So any of you, if you're interested, please write to me. Yes, I definitely want some one opening for PhD student, and also I also welcome. Currently, my lab only have one CSC, right? CSC visiting student in my lab. So I'm welcoming more to but I understand there's a limit of 2, right? Now there's a limit of 2 only. So which means each faculty can only host 2 students from China of this CSC under the CSC sponsorship. Okay, so but this is one of the fruitful collaboration with China, and I learn a lot from them. Yeah, welcome. Please do email me. You have my email, right? Just Google me. Just email me, and also I definitely welcome the collaboration. So this is always the one I always say, hey, within the forces, all men are equal. Okay, are brothers. Okay, so basically, so I as I said, I don't travel much, but I work a lot with China scholars, and this is Israel scholars, France, and this US, actually a lot more. Recently I have a lot more collaboration. Sun Xuemei from Beihang, I didn't include yet. A lot, because I think research is just, that's why I said this talk is the purpose of brainstorming. So let's just find out what from each other, what you can do, what I can do. So can we just work together efficiently? So we don't even need meet, right? We just need, nowadays it's very easy to talk online, Yeah. And many of them I haven't even met them yet, I mean, more than 60% of them, I don't know them. Just email them.
Yeah. I think this picture should be updated because Qihua has moved to Tsinghua University.
Oh, okay. But he's when he collaborated with me is in China, in Singapore. Yeah, I can change. Yeah, a great physicist. I'm very lucky. I learned a lot from him. Yeah.
Okay, so I think the time is up, and at last, on behalf of the Smart Mat, I welcome you to submit your best work to Smart Mat.
Sure,
This,
no problem.
young but very promising new journal.
Okay, thank you. Thanks for the invitation. Yeah, all the best to the new journal. Thank you. Bye-bye.
Thank you. Also, thank you for your
Bye, Professor Long. Thanks for your wonderful talk. Yeah, bye.
Thank you. Bye-bye.